I'm Dr. T. Welcome to my office. Today I'm doing a Q&A video. Questions come from April 25th, about 4 p.m. From class discussion boards and YouTube comments. Well, class discussion boards, there weren't any in the YouTube comments. So looking at the questions, first one is from an ISCI 202 board, or 2002 board. In this case, it's about cartography and chronology with respect to astronomy. So modern day, we are not really looking at the sky to figure out either of these two. So cartography, obviously map making, figuring out where you are and then hopefully using that to make a map or using a map, etc. Today we've got GPS satellites, which are awesome. I love my GPS. And then chronology, when are you? What time is it? Now we've got atomic clocks, good old mechanical clocks, all kinds of clocks, clocks upon clocks upon clocks. But back in the day, especially for prehistoric peoples, but honestly, frankly, even 20th century, and in some cases it's still a backup, we still have to look to the sky to answer those questions. So let's deal with timekeeping to start with. So if you're looking at what time it is, a lot of what you're really doing is trying to figure out where Earth is or where are you on Earth relative to other important things. So are you at a point that is pointing towards the sun? Therefore it is day. By looking at the shadows cast by the sun, you can measure the angle the sun is on the horizon and therefore what part of the day you're in, aka sundial. Now that's kind of the the classic one, but the other one you want to do is know where you are in your orbit. Is where you are in Earth's orbit determines what season it is, and how long, how far through that season are you, how soon until the next one kind of scenario. And for normal 21st century people, that's not a huge deal, but for those who are working in agriculture or in areas that are very seasonally dependent. And keep in mind, if you go back in time, a lot more people were working in agriculture. We didn't have the massive agricultural industry that we do now. Instead, it was, I have my crops growing kind of thing. Or I'm looking out the cave looking for when a nice tasty animal walks by kind of scenario. So in that case, seasons are very, very important. Where are the animals going to be if I'm a hunter? When do I plant? When do I harvest? When do I do what if I'm in agriculture? Even if I'm, doing a sailboat, when are the winds going to be favorable? The winds between, the coast of Africa and India, kind of that trade wind is very nice, cyclic. Sometimes they blow one way, sometimes they blow the other. Very regular patterns. Well, I need to know which way they're going to be blowing, so I need to know which way I can sail. Kind of scenario. So to do this, what we're going to do is look out, up into space, and we can see stars. Now, of course, as humans, we match stars to patterns, and because we're looking away from the sun, the ones that we can see tonight, in the spring, is going to be a different set of stars, at least in part, than the ones we can see in the winter. So knowing which ones we can see, where they are relative to each other and the horizon, specifically the horizon, then allows us to start figuring out where in Earth's orbit we are, what time it is with respect to seasons, and how to address them. Now, where we are on Earth. So this one, basically we're doing the same scenario, but we know reasonably what time it is, or we pick something that we don't really have to know. So we're looking like, okay, so the sun is setting, it's night. Where is the sun sitting on the horizon? That's going to start helping me know where I am with respect to latitude, how north or south I am. The farther north I go, it's going to be setting at a different point on the horizon than if I am towards the equator. I could do the same thing with stars as well. Now, knowing latitude, that's a little bit more difficult. So in that case, I'm going to have to measure the angle the sun is at noon, typically, or really a star. In reality, you can do this with any particular astronomical thing. But I need to know where it is where I'm at, and then where it is at my point of reference. And so for this, I need a good clock. And if I have a good clock, then that's usually pretty good. So this was the whole, the quest for timekeeping, the quest for the chronometer, which was a major, major invention. And there's been at least a couple of movies on this. Okay, so next set of questions come from my Survey 2 class, so Chem 1152. So first one, this is actually a fairly long list. Where does Augmentin fit into the arms race of bacteria? I am releasing a video today that covers this exact topic. So I will link to it here, and it will be on my channel and on the D12 page for that class. Where does the energy come from to link nucleotides together? So this would be DNA replication or translation with RNA. This comes from the triphosphates. So you have nucleotides, the ones that are being used are going to be in their triphosphate form, and being in their triphosphate form, you can break off the two phosphates, you're left with one, and you get a nice energy boost. So that's where you're getting all the power to do everything. How does ribosomes, codons, mRNA, tRNA interact to form proteins? Okay, this is a huge question. I've actually got a couple of videos that covers this, because this is DNA replication, transcription, post-transcriptional modification, and protein synthesis. So this is actually a lot. I will link the videos I have on this one. Okay, next one. Basically, when do we do fermentations? When we don't have enough oxygen. Once you're anaerobic, you ferment. Now, for humans, we can't get enough energy from fermentation. We will try, but we can't even come close. Because aerobic respiration with oxygen, you can do the electron transport chain, etc. That gives you so much more energy per glucose or per fatty acid or whatever you're burning. By the way, you can't ferment fatty acids. Anyways, let's see. If cell does not undergo fermentation, you're going to turn your glucose into CO2. Yeah, so if you're doing that one, you're going to do CO2 and water. The oxygen you inhale turns into water. The carbon from your fat, protein, carbohydrate, that all turns into CO2. What point can glycolysis no longer be reversed? It's when you lose that carbon dioxide. So once you go from pyruvate to acetyl-CoA, that is a one-way step. There is no going back. So yeah, that's a one-way step, at least for us humans. I mean, plants can, but plants are going straight from the CO2. So they're a very different kettle of fish. So that's a one-way step. It's pyruvate to acetyl-CoA. Once you're acetyl-CoA, there is no gluconeogenesis. That's no longer an option. Where does ethanol enter metabolism? It gets turned ethanol, ethanol, acetic acid, acetyl-CoA, boom, citric acid cycle. How does the electron transport chain relate to ATP production? Once again, I've got a video on that one. I'm going to link that one. So I'll link that. Okay, what's Vmax, Km, and how does this relate to enzyme kinetics? New video going live when I upload this one as well, so I will link to that. And what are the roles of metal ions in enzymes? So these are going to be cofactors. They could be structural components, or they could just be an actual catalytic component. So they could either be holding the enzyme together, or they could be involved in actually doing the chemistry, moving the electrons around. You see a classic case in the enzymes involved in nitrogen fixation, where you have iron and sulfur create this rather interesting complex that does some really cool electrochemistry to break the notoriously stable bond of N2. Okay, that's the questions I had as of 4 o'clock the day of recording. I'll be making a new video here not too long with more questions as they come in. With that said, have a wonderful day.